In this lesson, it's thermal energy and heat. I'm not going to go through it as one big lesson because it's a bit of a longer one. So I'm going to break this up into a few pieces and kind of explain a piece at a time. For a specific heat capacity, here's the definition. The amount of heat needed to cause a unit temperature change to a unit mass of substance. And I know what you're thinking, huh? What is he saying? Here is what this is saying. If I had a 1 kilogram mass, anytime we talk about a unit anything, what that means is mass is 1 kilogram. That's a 1. So mass is 1 kilogram. So here's my 1 kilogram mass. I want to cause a unit temperature change. So let's imagine T1, we start off at kind of room temperature, it's about 20 degrees, and I want to increase that to 21 degrees. There is my unit temperature, my 1 degree Celsius increase. Okay, so there's a unit temperature change for a unit mass. And the question is, what quantity of heat energy do I need to put in? So you could picture, you kind of put this thing on a flame or something. Here's a flame burning. And it's what quantity of heat energy is transferred into the object. So we use Q for quantity of heat energy. And the question is, how much heat energy is needed to raise this 1 kilogram mass by 1 degree Celsius? Turns out every substance has its own amount, and it's a constant. So gold, for example, has one quantity of heat. Iron has some different quantity of heat. Water has a different quantity, of heat. We can use this equation to kind of figure it out, but this C value right in here, that is the number that is kind of specific to every substance. Okay, so when we have this equation, Q is quantity of heat energy. All energies are measured in joules, at least for physics in the metric system. Energies are measured in joules for our purposes. Mass, we'll keep that in kilograms. In that case, the specific heat capacity is in joules per kilogram Kelvin. What that kind of implies is the change in temperature here has to be in Kelvin. And just a quick note about that. Anytime you have kind of Kelvin versus degree Celsius, what we have for this is they're just different by about 273 degrees, which seems like a weird number, but the Celsius scale is kind of based on water, right? Water freezes at 0, it thaws or boils, depending which way you're going, at 100 degrees Celsius. And is there a lowest point? Well, it turns out there is. Lord Kelvin, I guess, figured this out, and he figured it was negative 273 approximately. There's some decimals in there, but negative 273 Celsius. What he did then, Mr. Kelvin or Lord Kelvin, he said 0 Kelvin is going to be that absolute sort of lowest point, which makes this 273 Kelvin and makes this 373 Kelvin. Okay, so if you know your temperature in degrees Celsius, you can just add 273 and you're going to get your temperature in Kelvin. But what we can notice here is a change in temperature, a delta T of 100 degrees Celsius is the same as a delta T of 100 in Kelvin. So delta T, it doesn't matter whether we're using Celsius or Kelvin, it'll be the same in either case. That's good news for us, less converting. Let's actually try this out. While making Kool-Aid, Mr. G cools 2 kilograms of water, so mass 2 kilograms. Cools it from an initial temperature of 21 degrees C, that's in and around room temperature, to a fridge temperature somewhere around 5 degrees Celsius. I think my fridge is actually set at 4, but anyways. The question is, how much heat energy does his fridge pull out of that water? What quantity of heat energy? To know that, we have to know our C value. C value, this is a common one. This might be one that you start to kind of remember just from using it. But again, there's a table of these in your textbook. I can't remember if I wrote it down, what page number that is. But in this section, in section 5.3, if you flip through there, there's a section of C values or a table of C values. You can look them up online as well. It's called the specific heat capacity. And for water, it's approximately 4,200 joules per kilogram Kelvin. Just remember, this thing right here, we're going to need those T1 and T2 for our delta T. When we sub into this equation, we're expecting our delta T to be in Kelvin, but as long as I'm using those two temperatures in Celsius to find a delta T, then it's going to be the same value. Okay, so mass is 2 kilograms. The C value for water, 4,200. And again, I really want delta T as, which is, I should just say T2 minus T1, just as a reminder. I really want those temperatures in Kelvin, but because it's a delta, we're safe to do this. T2 is 5, T1 is, whoops, it's not, that's, I'm doing the math in my head. T1 is 21, which gives me a delta of 16. Let's find my calculator here. 2 times 4,200 times, well, let's say this first. Let's say 2 times 4,200 is 8,400. I just wanted you to see this. This would be minus 16 times 16. This is going to be negative 134,400 joules. What that means is this negative sign that's over here, okay, that negative sign right there, what that means is we're focusing in this question, we're focusing on the water, at least as far as our numbers. The question is asking how much energy does the fridge dispose of, but in all of our calculations we're focusing on the water. Okay, so that means the water loses this quantity of heat energy. But the question asks, how much energy does the fridge get rid of? Okay, so the fridge is pulling this quantity of heat energy out of the water and then kind of disposing it out the back of the fridge. What that means is the quantity of heat energy is, and we can do sig digs here as well, it looks like 3 sig digs, 1.34 times 10 to the 5 joules. That's we're changing it into a positive because of the way they ask the question. They ask how much energy the fridge kind of pulls out and gets rid of. So it's that quantity of heat, the fridge pulls it out of the water, dumps it out the back. And the answer given here is in kilojoules, same thing. So that's good.